We're starting a new unit today. So, Newton's laws of motion. So, while most people while most people know what Newton's laws say, many people do not know what they mean, or simply do not believe what they say. So, Newton's laws of motion. The first law, an object at rest will stay at rest. An object in motion will stay in motion at a constant velocity, unless acted upon by unbalanced force. Force equals mass times acceleration is the second law. So the second law relates force, mass, and acceleration. And the third law states for every action, there's an equal and opposite reaction. Have you all seen these laws before? So in this class, we'll delve into them probably deeper than you did in previous class. So, the first law of motion, and this just repeats it, states that the law of the first law of motion is also known as the law of inertia. Again, this just repeats what it says. So, law of motion, first law, an object at rest will stay at rest. An object in motion will stay in motion at a constant velocity unless acted upon by unbalanced force. So an object in motion will stay in motion at a constant velocity. We'll get to that second. Note it does say velocity, not speed. I told you that there's an important difference between velocity and speed, and here is where it's going to come into account. So the first law deals with inertia. Inertia is the tendency of an object to resist changes in its velocity, whether in motion or motionless. So, for example, so inertia is directly tied to mass. If you have more mass, you have more inertia. If you have less mass, you have less inertia. So, for example, if you were to have a nearly empty shopping cart and you were to push it as hard as you can, how far do you think you can make it go? It'll go good ways. So having less mass, less inertia, means it's not going to resist the change in motion too much. You'll be able to push it and watch it go a good bit. Now imagine if you take several hundred pounds and put it into the shopping cart, and then you pushed it as hard as possible. How far do you think it would go now? So not very far. So the more mass or more inertia something has, the more it will resist the change in motion. So you applied some force, and if it has a high inertia, it's going to resist changing. So looking at this example, so if you have a golf ball, once airborne, unless acted upon by unbalanced force, it will never stop. So if you were to hit a golf ball, and assuming that there is no external forces, it will continue moving forever and ever. By the way, I don't know if I did it in this class yet, but is air a fluid? What does it mean by, what does fluid mean? If I say your movement was very fluid, what do I mean? Constant, no? Smooth? Oh, so what's a better way? So if I say someone like very fluid, it's like smooth, starts with FL, flows. A fluid is something that flows. Does air flow? So you can feel wind flowing past you. Do liquids flow? Yes. A fluid includes both gases and liquids. So all liquids are fluids. All gases are fluids. We just usually mean when we refer to fluid, it's just liquids. But air is also a fluid. It can flow past you and move out of the way. Is a block of gold a fluid? If you try to put your hand on top of it, will it flow past your fingers? No. So solids are not fluids, but gases and liquids are. We'll learn more about the different types of frictions, but the reason why a golf ball doesn't continually move forever is because of friction. Particularly air friction will slow it down in the air. If you were in space and one of the astronauts took a hammer and threw it out of the International Space Station, that hammer wouldn't move forever unless it collided with the Earth or the Moon or somewhere else. It will continue moving in a straight line. If they were to take a wrench and spin it, it will spin in a circle for all eternity unless it falls back down to the Earth or some other external force were to happen to it. So without air resistance, things will always continually move. So unless acted upon by unbalanced force, this golf ball would sit on the tee forever. Objects do not start moving by themselves. There has to be some external force causing it. If something is at rest, it will stay motionless for all eternity unless some force acts upon it. So if you were to set something down on a hill and it starts rolling down the hill, why did it start rolling? Because the force of gravity pulls it down the hill. And it's only because there's a force acting on it that it actually start moving. So why then do we observe everyday objects in motion slowing down and becoming motionless seemingly without an outside force? It's because of the force of friction. We can't see this force, but it's there. We have air resistance. So if you throw a basketball or a baseball in the air, it'll eventually slow down. If you were to jump off of the Empire State Building, air resistance would actually slow you down, and there's actually a max speed. There is no difference between falling out of an Empire State Building versus falling out from an airplane 100 miles up in the air. This is because air resistance will slow us down and make us reach a certain terminal velocity. Objects on Earth, unlike frictionless space the Moon travels through, are under the influence of friction. So the reason why the moon constantly orbits around the Earth is because there's nothing in front of it to slow it down. There's no friction. So the moon will continue to orbit around the Earth for basically ever. It's way outside of the scope of this class, but technically there's something else that will slow down the moon. It's called gravitational waves. You might have heard of it. Has any of y'all heard of gravitational waves? They were just recently detected a few years ago. It's where the fabric of space ripples. So it's very advanced stuff though, outside the scope of this class. So let's look at different types of friction. There are 4 main types of friction. There is sliding friction. So if you have a box on the ground and you were to push it, it's a flat surface touching another flat surface and they're rubbing over each other. So this is known as sliding friction. It's the reason why if you push a box, it'll eventually come to a stop when it's sliding across the floor. Also, ice skating is an example given here. If you're ice skating, you would eventually come to a stop because the blades are sliding across the ice. We also have something known as rolling friction. The reason why a car, if you let off the gas, can come to a stop. It's because of the friction between the tires and the ground. Whenever the wheels spin, there's a friction force on it, which slows down the car. Rolling a bowling ball also. Bowling ball will eventually come to a stop when it's rolling, and this is known as rolling friction. We also have fluid friction. Fluid friction includes both air and liquid. So we have air resistance and we have water resistance. If you run in a boat and your engine were to cut off, you would come to a stop very quickly because the water is resisting the flow. It's exerting a force on the boat. Then we have static friction. So if y'all learned about chemicals and molecules and bonding to some degree, y'all know that there's atoms and atoms bond with other atoms, right? So static friction, whenever 2 surfaces touch, the atoms on one surface will loosely bond with the atoms on another. And in order to get something to move, you have to overcome the static friction. The static friction occurs because there's slight little bonds. Have y'all ever seen that thing where you take 2 phone books, interlace the papers, and then we're able to lift up an entire car using just a phone book? All it does is uses friction. Each page is loosely touching the other one and can't slide past each other. Sliding friction is the initial friction you have to overcome to get something moving. So in order to get something actual moving, you have to overcome this static friction, and it's due to breaking the loose bonds between surfaces. So sliding a book across a table and watch it slide to a rest position. The book comes to a rest because of the presence of a force, that force being a sliding friction, or a force of friction, which brings the book to a rest position. So if you were to slide a book across a table, it will come to a stop because of sliding friction. If there was no friction, the book will continue moving at whatever initial speed it started at. So in the absence of the force of friction, as soon as you push it and it starts moving, it will move with the same speed and direction. It will never turn to the left, it will never turn to the right. So Newton's first law says constant velocity. Velocity includes both direction and speed. So unless you do use a force on something, it will stay going in a straight line, never deviating or turning forever. Or at least until it goes off the surface of the table and gravity catches it and pulls it down. So Newton's first law. So if you're in a car going 50 miles per hour, and the car hits a brick wall and comes to a stop, you're still moving 50 miles an hour. Unless you have a seatbelt on or something to stop you, you will continue moving at whatever speed you're currently going at. I have a question for y'all. Do y'all think going 15, 20 miles an hour is safe to not wear a seatbelt? So going 15, 20 miles an hour and not wearing a seatbelt, if your car were to come to a sudden stop, it would be the same thing. Do y'all know who Usain Bolt is? Fastest runner. He can run, I think his top speed was like 28 miles an hour. Usually most people, the fastest runners in the world, they top out around 20 miles an hour. 20 miles an hour is really insanely fast. So, if you were in a car going 20 miles an hour without a seatbelt, to us it appears really slow because we're used to going much faster than that. But it's the same thing as going 20 miles an hour, running as fast as you possibly can. So y'all probably can't run 20 miles an hour. So imagine running as fast as you possibly can and straight into a brick wall. That would be the equivalent of riding in a car without a seatbelt, even though you're going that slow, and slamming on the brakes or hitting something and coming to a complete stop. You will be moving forward at wherever your speed is. So even if your speed is only 10 miles an hour, imagine running straight into a brick wall at 10 miles an hour. People have actually died if they hit their head against something. Having your head collide into your steering wheel or the front windshield at 10 miles an hour is enough to cause you a concussion or brain damage. So because of inertia, because you resist the change in motion, if you're going 50 miles an hour and your car stops, your mass is going to resist changing from 50 miles an hour. You're going to want to continue moving at 50 miles an hour. So this brings us to the second law. Force equals mass times acceleration. So the second law states that force is equal to the product of mass and acceleration. So the net force of an object is equal to the product of its mass and acceleration. Rf equals ma. When the mass is in kilograms and the acceleration is in meters per second, also known as meters per second squared, the unit of force can be written in the units of newtons. A newton is equal to a kilogram times a meter per second squared. So 1 newton is equal to the force required to accelerate 1 kilogram of mass at 1 meter per second squared. Hello? I was going to do it next week. Yeah. Bye. So 1 newton is equal to the force required to accelerate 1 kilogram of mass at 1 meter per second squared. So we got a new equation. Let's do an example with it. For the kids at home, that's the code word. So the code word is this. Yeah, I don't need to see it. So that I can see that they watch the videos. Apparently people have been texting fellow students, and students have been telling them the code words. So, how much force is needed to accelerate a 1400 kilogram car 2 meters per second per second. So how much force is needed to accelerate a 1400 kilogram car 2 meters per second per second? So we have our equation. Force is equal to mass times acceleration. We can convert this into a triangle. Where does F go? It goes to the top. And mass and acceleration would go to the bottom. It's already set up for force. We're trying to find force. So now let's identify the variables. So 1400 kilograms is our mass. Our mass is 1400 kilograms. And this would be our acceleration. So our acceleration, 2 meters per second squared, or 2 meters per second, can be written as 2 meters per second squared. You can combine the per second twice. That's what this second squared means. It means per second. And so force is equal to 1400 kilograms times 2 meters per second squared. And that would give us 2800, a kilogram times a meter per second squared. Now, if we remember what it just said, it said that kilogram and a meter per second are kilogram times a meter per second squared. We can replace this with a newton. So we can replace this with newtons. I'm going to try to keep everything from now on in just meters, seconds, and kilograms. So your force is going to always be measured in newtons. Your mass, it's going to either be in kilograms or grams. And your time is going to usually be in seconds. You still need to convert, like if I asked you in a minute, you'll still need to convert minute into seconds. But does this make sense? So let's do a table. So net force is if we have a net force of 10, or I should say if we have a mass of 2 kilograms and an acceleration of 5 meters per second squared, then our force is going to be 10 newtons. If we have a mass of 2 kilograms and we double the acceleration, so we could take the acceleration from 5 meters per second squared to 10 meters per second squared, we would double the force from 10 newtons to 20 newtons. So what would go in the middle blank? Yes. So we have force equals 20 newtons, and we'll have a blank for the mass, and we have acceleration of 5 meters per second squared. So we know that force is equal to mass times acceleration. So force is equal to this times that. So what times 5 gives you 20? That'd be 4 kilograms. Another way we could have done this, if you didn't know how to do that, so this basically says what times 5 gives you 20. We could have started with our equation. So F equals ma, and we're trying to solve for mass. So mass is equal to force divided by acceleration. Or force is 20 newtons, or acceleration is 5 meters per second squared. This is equal to 4 newtons divided by a meter per second squared. And as I said, all you really need to know is that our force, or mass unit, if we have meters, if we're in meters, if you just see meters, seconds, and newtons, then our mass is going to be this. This represents kilograms. So if we're solving for mass, our answer is going to be in kilograms. If we're solving for acceleration, our acceleration is going to be in meters per second squared. And our force is going to be in newtons. So when you say what times 5 equals 20 is the exact same thing as saying 20 divided by 5. That is your what. 20 divided by 5 is your equal to your what in that expression. So 1 kilogram times 10 meters per second squared gives you 10 newtons. What? If we wanted to solve, what would acceleration be in the second to last column? So we have 10 newtons, we have 5 kilograms. What would be the right side? It'd be 2. So 2 meters per second squared times 5 kilograms gives you 10 newtons. So last slide that we're doing today, then we're done. Newton's second law proves that different masses accelerate the Earth at the same rate, but with different forces. Did y'all know that in the absence of air, if you had no air resistance, you could drop a car and a feather off the Empire State Building and it would fall and hit at the same time? So with you can take a sheet of paper and a bowling ball, and without any air resistance, they would fall at the same speed. Or same acceleration. Things accelerate at the same rate regardless of their mass. What changes is the amount of force. So we know that objects with different masses accelerate to the ground at the same rate. So they'll both reach the ground at the same time if you ignore air resistance. However, because of the second law, we know that they don't hit with the ground with the same force. So when things hit the ground, it does. The acceleration will be the same. What changes is the amount of force. So if you drop if you drop a baseball on your foot, probably nothing really bad would happen. However, if you drop a bowling ball, it might hurt a lot. If you didn't know this, the acceleration due to gravity on Earth is around 9.8 meters per second squared. This is roughly about 10 meters per second squared. So if you were to ignore air resistance and you were to jump off a very tall building, after 1 second, your speed would increase from 0 to 10 meters per second. After another second, it would add another 10 and become 20 meters per second. After another second, you would be at 30 meters per second, roughly. So on Earth, things fall at the rate of about 10 meters per second every second. So does that make sense? By the way, I should say, so imperial units are weird. Our imperial units are feet, pounds, inches, miles. Does anyone know what the old imperial unit for mass is? So in metric system, we use the meter, or mass is measured in kilogram, and our weight would be measured in newton. In imperial units, we measure weight in pounds. Does anyone know the name of the unit we measure our mass in? Slugs. If you've never heard of a slug, that's because scientists don't really like the imperial system. And the only time you need to know mass is in science. We tend to avoid using the imperial system in all sciences. We stick with the meter, the newton, and the meter per second squared for acceleration. Next time we'll look into gravity and the equation associated with it. But that's it for today.